We had already seen this familiar example where we had got 6 plots 1, 2, 3, 4, 5, 6 as identical as possible, and we had 3 varieties that we called 1, 2, 3. We picked up 2 of the plots at random, sowed variety 1, and 2 remaining plots randomly variety 2, and in the 2 remaining plots we sowed variety 3, continued for 1 season, then harvested and measured the yield. Now when we do this, the model that we used was this. So we had this Yij equal to mu plus alpha I plus epsilon ij, I going from 1 to 3, I is for the variety, j is for the random error, and epsilon ij 0 sigma square, and all these are the parameters. So we have the coefficient parameters, there are 4 of them, mu, alpha 1, alpha 2, alpha 3. They are all real valued, they may take any value in R, and we have sigma square unknown. Everything is unknown, but sigma square is also positive. Now suppose we ask a very important question in such a setup, that is, are the varieties really different? So do they really differ in terms of their yield? That is typically the primary question that we shall ask. Now, if we want to ask this question, we are basically trying to make a test of hypothesis, where the null hypothesis is that they are not making any difference, and the alternative is yes, they are making some difference, that is, at least 2 varieties are different. Now, what is the null model? So, under the null distribution, we are basically saying that we have shown effectively the same thing over all the things. So the varieties do not make any difference. So effectively we have got only one variety, so to speak. So in that case, the model will be like this. We have got Yij equal to mu plus epsilon I. I do not have that alpha I term at all. I have only mu plus epsilon I. Everything else is essentially the same. Only the number of coefficients now is only mu and sigma square. So only 2 parameters to estimate, whereas here I had 5 parameters to estimate. Now be careful here. When excuse me, I am saying that this is a model, I am actually giving a family of distributions, where this mu, alpha 1, alpha 2, alpha 3 are actually the indexing parameters. So set of all such things where mu, alpha 1, alpha 2, alpha 3 are in R and sigma square is positive. So these are the index parameters. So the index parameter here and the index parameter there, they do not have any relationship. So do not think that the mu here is same as the mu there. They are just index parameter. It is just like saying I can represent the entire R as all x cube when x is in R. The set of all x cube when x is in R. That denotes R. Similarly, I can write the set of all x to the power 5 as x is in R. That is also set of R. So I can say that these 2 sets are equal. But that does not mean that x cube is equal to x to the power 5. X is like the dummy variable. It is the indexing parameter. So though I am writing the same mu, the same epsilon, the same sigma square here as well as there, but this does not mean that they are the same things. So if over the same model I fit this and I fit that, the 2 mu hats that I will get will of course be different. The only thing that is common to both of them are the Yijs. For the same Yijs, I am claiming this model is a good fit and that model is a good fit. So the basic idea that we are going to discuss in this and some subsequent lectures is the idea of test of hypothesis in the context of linear models, and this is one example of that, where I have this full model and I have a restricted version of the same model. Observe that this is a restricted version. If you put all the alpha is equal to 0, then you get this. Or you might think of it like this: if I put all the alpha is equal to some constant number, then also I get a model like this, because the constant may be absorbed inside mu. So I can think of this, that this is a family, this is a set of distribution, that is another set of distribution. This set of distribution is a subset of that set of distribution. Such a situation is sometimes called restricted model, sometimes called nested model, and that's what we are going to specialize on. Now there is something special about this subclass of model and this class of model. So this is, as I said, a set of models, in the sense that this is a subspace of that, not just a subset of that. To understand this, we just consider the design matrix. So the design matrix of that model, as you can easily see, is for the mu's I have got 1, 1, 1, 1, 1. For the alpha 1s, that is for the things where you have got variety 1, you will put 1, 1 and 0, 0, 0, 0, 0. Then 0, 0, 1, 1, 0, 0. This is for alpha 2, and 4 zeros followed by 2 1s, that's for alpha 3. So that was the design matrix. Now think of what is going to be the design matrix in this case. For that, the design matrix will be 1, 1, 1, 1, 1. So observe that this design matrix, the column space of the design matrix, is a subspace of the column space of this design matrix. So that is what we are going to work with. So we will be given two models. Here is my first model, the model which we believe is already a good fit. Just observe that I have added one extra assumption here. I have assumed that the epsilons are not only mean 0 and variance sigma square I, but they also happen to be jointly normal. That is the typical assumption under which we will perform our test, because we need the distribution of the test statistics, so we need a full distributional assumption, and the normal distribution assumption is the most natural one, because it makes mathematics simple, not because that is the most commonly occurring thing or anything, but that's a popular choice. So we will be given one set of model, so one model, which basically means a family of distribution, and we believe that it is a good fit. What does that mean? This means the true distribution of our data lies in or pretty close to this thing, or I might say not pretty close to, it lies actually in this family. So y will lie pretty close to column space of X, but that we are assuming that this is based on whatever goodness of fit we have done, etc. We are now happy based on domain knowledge, goodness of fit, diagnostics, etc., etc., that we are happy that this is a good fit. We are ready to give it, clinch it. Now someone gives us a restricted set of model, same thing as this, except that now we are working with some x1 instead of that x. x1 does not need to be made up of only columns chosen from columns of x. It may be just a different design matrix, of course, design matrix completely known and fixed, such that we have essentially the same type of assumptions here also, but as I have mentioned earlier, the beta here is nothing but an indexing parameter. So the beta here and the beta here are possibly different. You can see that here I said beta lies in Rp and here I said beta lies in Rq. That is, I am assuming this x is n by p, whereas this x1 is n, same n, by q. N remains the same because our observation vector, the data, remains the same. And I assume that column space of x1 is inside column space of x. That is what I say, what I mean when I say that this model is a subspace of that model, not just a subset. So it is again a linear model. So I have a column space here and a column space there. This column space lies inside that column space. One simple way of thinking is that it is possible to put restrictions on this beta such that this model reduces to that model. As in the last example, if I put the restriction that all the alpha I is equal to 0, all the alpha I is equal to 5, then the first model reduced to the second model. And that's a simple proof that the second model is indeed a subset or subspace of the first model. Now the column space of x1 is a subspace of column space of x, but that does not necessarily mean that the columns of x will form a subset of the columns of the columns of x1 will form a subset of the columns of x1 of x. That is, you are not picking certain columns of x and creating x1 by stacking them. So here is one example where that is not the case. Suppose we are again working with the same model, mu plus alpha I plus epsilon ij. So we have this 1 1 1 1 1 0 0 0 0 0 1 1 0 0 and 0 0 0 0 1 1. Now I am trying to test the hypothesis whether the first two varieties are effectively the same or not. So that is what we are trying to test, whether the first two varieties are the same or not, which means I am basically testing alpha 1 equal to alpha 2 or not. I am not caring about alpha 3 at all. That still remains unrestricted. In that case, my design matrix will become this. Once alpha 1 equal to alpha 2, that becomes a common parameter. So this is, as before, my column for mu. This column is devoted to that common parameter. You might call it just alpha. And this is, as before, devoted to alpha 3. So how did I get this? Very simple. I just added these two columns. So for all the plots where the first thing has been shown, they will have this common effect alpha, and for all the plots for which I have got variety 2, they are also alpha 2, but alpha 2 is same as that new alpha. So these two columns are kind of merged. That is, in this case, they are just added as two vectors. So here again, this is my x1 whose column space belongs to column space of this, is contained in column space of this, but observe that this new column 1 1 1 1 1 0 0 is not one of the columns of this matrix X. So it is obtained as a linear combination of two columns, but it is not directly a column of the X matrix. Now in this video, we are not going to go into all the mathematical details of how we shall carry out the test, but we shall give only the basic idea, the heuristics, to show what is the most natural way of testing it, what is the natural tester testing. And for that, it will help if we just look at the entire thing pictorially. So we start with our familiar picture where we have got this column space of X and our data, this vector, this data, and we have also got this residual vector. Now we are working with, that is my origin. So this is my origin here. Now we are working with a subspace of this column space of X, which I will denote by this line. So this is my subspace. This is my subspace of column space of X. This is so this is column space of X1. So what is the natural way of carrying out this test? You basically fit this restricted model as well, and that means you are dropping a perpendicular from the data tip to this new subspace, that is a perpendicular, and you are basically seeing this is the error that I am committing if I am going for the null model, the restricted model, the model that is propounded by the null hypothesis, and this is the error that I was anyway incurring. Now carefully understand this thing here. When we say that I already have this model, this makes a strong statement. This basically says that you have carried out your goodness of fit test, taken care of your domain knowledge, etc., and said that this is a good fit, this entire pink plane is a good fit, which means that this amount of error is acceptable. So you are making the claim, I am happy to live with this much error. Now the question is, you are getting this error. So definitely this error is more than that error, because you have restricted the model, so you can never expect your error to go down. So error must go up, either goes up or stays wherever it was. So your question now is whether this particular thing is acceptable also. So for that, what you will look at is what is the extra contribution. Now observe that here we have a nice little right angle triangle. So this is my extra contribution, in the sense I am working with the squared norm. So if I take squared norm or the RSS for the restricted model, from that subtract the squared norm of my basic model, my base model, which I know is correct, in that case I will get the squared norm of this vector, applying a little bit of Pythagoras, of course in higher dimension. So I get this. This is the extra thing. So this is what is already acceptable, and this is what is extra. So it is something like this. Say I earn 100 rupees per month, and then I have to, so I am spending something for some purpose, and I now have to spend 50 rupees extra for that purpose. Now if it is something like I get only 100 rupees salary per month, then spending extra 50 rupees will mean a lot. If on the other hand I earn 1 lakh rupees per month, then spending extra 50 rupees does not matter much. So it actually depends on what is acceptable and what you are paying extra. So someone who is trying to buy an air ticket and is already spending 30,000 for that, if that price goes up by 500 rupees extra, you hardly care. You are often ready to pay that amount as a convenience fee. On the other hand, if you are trying to buy some bananas and there the price increases even by 1 rupee per banana, you start haggling and bargaining. That seems very unfair. So we are always working with relative error, so to speak. So this extra thing must be measured with respect to the yardstick of what is acceptable. Now let us just turn these things into a little bit of mathematics. So this one is what we call the RSS, the residual sum of square. That was the acceptable thing. We first fit the base model, the model which we know is a good fit, and then we fit that restricted model to get this vector, this oblique thing, and that residual sum of square we call RSS1. We subtract one from the other, and we are trying to see whether RSS1 minus RSS is significantly large compared to RSS. That is important. We cannot absolutely threshold this quantity. We have to do it relatively. So what is the most natural thing but to work with RSS1 minus RSS, the extra thing, divided by this accepted thing, RSS. So you are basically expressing the extra thing in unit of what is acceptable. So how many acceptable units am I adding extra? Naturally, if this number is large, you tend to believe that no, my extra error is too much. And if this is small, then you are happy. So intuitively, this should be our test statistic. And indeed, that is the test statistic. And not only that, this has two additional benefits. One, if you just carry out the idea of likelihood ratio test, which is a very routine way of constructing a test in any given situation, if you blindly follow that, then after some linear algebraic jugglery, you will find that that is precisely the test statistic that you get. That is one nice thing about it. So it has got some theoretical justification also apart from the heuristic justification that I just mentioned. The other thing is, once you have this test statistic, you will be interested in finding its distribution, especially its null distribution under the null hypothesis, because you have to find critical value, p-values, etc. In general, that may not be a very easy problem, but in this case, under the Gaussianity assumption, you will find that this has a very nice standard distribution. It will have an F distribution. Well, I would qualify that remark a little bit. A scale version of that, after you divide by suitable degrees of freedom, that will become an F statistic. Not only that, it will have an F statistic, F distribution under null hypothesis as well as under the alternative hypothesis. And alternative hypothesis means that the X1 is not possibly a good fit. So X1 is not a good fit, and X is of course always a good fit. So under null hypothesis, the F will be a central F, and under alternative it will be a non-central F, but we shall take up all those things in a later video.